We're going to look at a proof of the irrationality of root 5. This is a very common form of proof. You might well be expected to prove that certain surds are irrational. The classic irrationality of root 2 is one that you've probably seen in the classroom, and trying one with a slightly different number will help you to see what's similar and what's different between the different forms. The first thing to notice here is that we are doing a proof by contradiction. To prove something like that a number is irrational, generally speaking, it's easier to prove that it's not possible for the number to be rational. So we start with a negation statement. The negation is something which should be true precisely whenever the other thing is false, and false whenever the other thing is true. In other words, if we can set up a statement which is the exact not of the original statement we're trying to prove, if you like, that root 5 is not irrational, if we can prove that that is somehow false, then we've proved that root 5 is irrational. So we're going to do this. We're going to assume that root 5 is rational. In other words, root 5 can be written as a over b, where a and b are integers. There's an important extra detail that comes in here as well. Also, assume that a over b is written in its simplest form. This may not seem like an important detail, but it turns out to be the thing which our proof by contradiction hinges upon. Another way of saying this would be a and b are co-prime. That's just a fancy word for they share no common factors, or more technically, no factors in common other than 1. Or you could just say their highest common factor is 1. In other words, the fraction can't be written any more simply. You can't divide down. A and b have nothing in common with each other factor-wise. That turns out to be important because we're going to go on to prove that a and b in fact do share a common factor whenever a over b is equal to root 5. And since they can't simultaneously share a common factor and not, that is going to be how we show that our negation is actually false. So now we're going to do another really common thing that happens within a proof. We're going to use the fundamental definition, the defining features of what we're working with. We've already used the definition of rational, that is, can be written as a over b where a and b are integers. Now we're going to use the defining feature of root 5, which is that if you square it, you get 5. Seems logical enough. And that means that a over b squared is 5. We can write this as a squared over b squared equals 5. And then if we multiply both sides by b squared, that's going to be helpful because, well, we don't have any fractions left anymore. And in fact, now we have an equation where both sides are integers. Remember, a and b are integers, so a squared is an integer and 5 times b squared is an integer. Not only that, but we can now say something important about a squared. A squared is a multiple of 5. We know that for sure because a squared is equal to 5 times an integer. B, whatever b is, it's a whole number. When you square it, you get another whole number. If you multiply that whole number by 5, you get a multiple of 5. Now this next step, sometimes you need to prove in and of itself, sort of a mini bonus proof by contradiction inside here. And there are a few ways to prove this section. But I'm going to say here that if a squared is a multiple of 5, then a is a multiple of 5. And as I said, you can prove this by contradiction. You can say, let's assume it's not a multiple of 5, and then try squaring it, and you'll find that what you get when you square it can never be a multiple of 5. But the simplest way to prove this one is probably to say, since if a has no 5s in its prime factorization, neither does a squared. If you imagine a as being made from a bunch of prime numbers multiplied together, if you square a, all you do is you double the number of each of those primes. So if a were 12, 2 squared times 3, when you square it, you get 144, 2 to the 4 times 3 squared. All that's happened is we've got twice as many of every prime factor. We've not introduced any new prime factors. So this kind of claim will work whenever the number we're dealing with is a prime. And this is the reason that the proof breaks down if you try to prove that root 4 is irrational. Because it's perfectly possible to have a squared being a multiple of 4, but a not being a multiple of 4. As long as a is a multiple of 2, then a squared will be a multiple of 4. So this is kind of important to the whole idea that we're working with. Now, if a is a multiple of 5, we can replace a with something like 5k. If a is a multiple of 5, it's equal to 5 times some integer. But that means that our equation a squared equals 5b squared becomes 5k squared equals 5b squared. Although you can't hear it when we say this, 5k in a bracket squared is different to 5b squared without any brackets. More precisely, if we get rid of the brackets by squaring 5k, we do 5k times 5k, that's 25k squared. That is equal to 5b squared. Now that in turn can be simplified one step further. 5k squared equals b squared. And that should look familiar. We just had 5b squared equals a squared. Now we have 5k squared equals b squared. That means that b squared is a multiple of 5. And now we're getting on to the final bit of our proof. So we've managed to show that a is a multiple of 5. I'm going to put that in bold. But we can now say, since b squared is a multiple of 5, b is a multiple of 5. We don't need to explain all over again why that's true. We explained it here, and the logic is the same here. But the key thing here is that a and b are both multiples of 5. We can say a and b have no common factors other than 1, or a and b have highest common factor 1. Or we can just say a and b are coprime. However we want to say it, we are flagging up the fact that this claim has been thrown out entirely by the contradiction that has just become apparent. A is a multiple of 5, and b is a multiple of 5, but a and b are coprime. Those statements cannot coexist. Usually we use the word contradiction or a symbol that means contradiction, and from that point we can just give our conclusion. Since the negation has been proved false, remember that this assumption here, assume that root 5 is rational, that's the only claim we've made. Everything else follows from that. And since that claim has been proven to end in a logical impossibility, two things that cannot both be true must both be true, therefore we conclude that root 5 is irrational. And that's the end of our proof.